Hello viewers, today we will see the Norton's theorem and its application to the DC resistive networks. I thank you all for viewing my earlier videos on other theorems and also on the Kirchhoff's laws. Those who are seeing this video, I just remind them that my other lectures are there on Kirchhoff's law, superposition theorem and Thevenin's theorem. Before studying the Norton theorem, I just request you all to first go through initially the lecture of Kirchhoff's law, and then thereafter you please go through the lectures on Thevenin's theorem. The reason is that it is said that the Norton's theorem is complementary to the Thevenin's theorem, and also we can say that Thevenin's theorem is complementary to the Norton's theorem. There are certain similarities in the operating procedure of both these theorems. That's why it is very necessary to understand the steps that we have used in solving the problem with Thevenin's theorem. So certain steps are exactly same and certain steps are similar. Okay, so they are said to be complementary to each other. Of course, at the end we will make some remarks after finding out the solution and after implementing these steps. So let us move to the Norton's theorem. Now see, again we have taken the same problem which we had taken for the Thevenin's theorem, for understanding the Thevenin's theorem. So the same circuit I have taken, but the problem statement is again changed. The problem statement is find the current in 8 ohm resistor, this one, using now Norton's theorem. Okay. So please see the first video of earlier video on Thevenin's theorem. Now see here, I had told in the earlier video of Thevenin's theorem that we can solve any such problem by using 5 simple steps. Here also there will be 4 or say 5 simple steps which we can use for finding out the final solution. Our problem is to find the current in this 8 ohm resistor, but we have to use Norton's theorem. Now see, the step 1 is same. Step 1 here is same as the step 1 in Thevenin's theorem. The resistor or the component in which we want to find out the current, we have to remove it from the circuit. That is the step 1, which is exactly same for both Thevenin's theorem and the Norton's theorem. So what is our resistance? The resistance is 8 ohm. We want to find out current in this 8 ohm resistor. So we will call this resistor as the load resistor or RL, and we will then remove it from the circuit. So after doing this 8 ohm resistor, we just get the things like this. So I just remove it from the circuit, and then exactly in the same manner as we did in Thevenin's theorem, we just mark these open terminals with A and B. Okay. So what is the first step in Norton's theorem? The first step in Norton's theorem is to remove the resistance in which we want to find out the current, and we have to denote it as load resistor RL. And then whatever open terminals we get, we have to mark them with suitable letters like AB, MN, XY and so on. Okay. So I have just removed it from the circuit, and somewhere here I will write that our load resistor RL is 8 ohm. Okay. So this step is exactly same. Now we get something here after removing the load resistor. We call this type of circuit now as a 2-port network. Okay, so I will just enclose the entire network into such a box. Okay, so suppose like this. So we get the 2 open ports A and B, and then there is the remaining entire circuit which is enclosed in this red line area or red line space. Okay, now this was the step 1. Again see what is the central idea now. Central idea of the Norton's theorem. Okay. In Thevenin's theorem, what we did was we converted this particular circuit into the red space with the help of, or say in terms of, some equivalent voltage source V.Tech like this, called as a Thevenin's voltage, and then one single equivalent resistance RTH. Okay, and so this was our point A and this was our point B. So this was done in the solution with the Thevenin's theorem. So what we did in Thevenin's theorem was the entire circuit in this box was finally represented with a single equivalent voltage VTH and the single equivalent resistance RTH. And then later on we substituted or reconnected the load resistance across these 2 points. So that was the central idea of the Thevenin's theorem. See here, what is the difference here? In Norton's theorem, Norton suggested that whatever we get into the space enclosed by the red line, we have to convert it into the equivalent circuit in which instead of voltage source, there will be a current source. So it would be like this. So instead of voltage source, that would be a simple current source like this. Okay. So maybe shown like this. Okay. So the idea is to convert this entire circuit into single equivalent current source and to be shown here like this. And then second thing into Norton theorem is that across these 2 points, the circuit, this entire circuit would give some single equivalent value of the resistance. Also we have seen it in the Thevenin's theorem. Okay, and we called it as RTH. The same concept is here. Here also this step is exactly same as the step to find the RTH. So we have to find a single equivalent resistance across points A and B, okay, for given by this entire circuit. But that time we have to consider this circuit only as a passive circuit. That means the power sources are not acting. Let there be the voltage sources or current sources. We just replace them. There is simple idea to make this entire circuit as passive. What is the idea? Idea is if there is an ideal voltage source, we have to replace it with a short circuit. If there is an ideal current source, then we have to replace it with open circuit. But if these sources are practical sources in the given circuit, then we have to replace both voltage or current source with their internal resistances. So only 3 basic things to make this circuit passive. For ideal voltage source, a plain short circuit. For ideal current source, a simple open circuit. And if these sources are not ideal one, both voltage as well as the current source, but if they have some internal resistance, then we have to replace the sources with their internal resistances. So that is the idea. So here we find some single value of equivalent resistance given by the entire passive network enclosed in this red enclosure, red line. And then we connect this resistance not in series like this, but we connect it here in parallel with the current source. So the things will be represented like this. Okay. So this is the central idea of Norton's theorem. Norton suggested that we have to convert this entire circuit into a single equivalent current source and to be shown like this. And we have to convert, or say we have to represent the entire passive network in terms of some resistance which is to be shown parallel to the current source. Let us give some names to these 2 values. Suppose whatever current we will calculate and to be shown here, that current we say that it is IN. Now remember, in Thevenin's theorem there was VTH. TH was the initials of Thevenin. Here, since this is a Norton theorem, we will just have a practice of taking this suffix as a capital N. Okay, so IN will be this equivalent current source. And here the resistance, we just call it as RN. Remember, this RN, the concept or the meaning of Rn here is exactly same as the meaning of RTH in the Thevenin's theorem. But what is the difference? Difference is that in Thevenin's theorem, you calculate VTH. What was the meaning of that VTH? The meaning was the open circuit voltage across these 2 terminals. That was VTH. And what was RTH? RTH was the equivalent value of this entire passive network as seen from these 2 terminals. Here what are the meanings now? Here the meaning of IN is that, now see, this is very important point. Meaning of this IN value is that if for the time being or for temporarily we short these 2 points like this, what we are doing, after we get the 2-port network, means after removing the load resistor, we get a 2-port network, means these 2 open terminals. if temporarily we short these two terminals straight A to B, a short circuit. So this is a short link, shorted link, like this. So if we short these two open points, and then if we see or if we calculate what would be the current in this short circuited link, some current will flow here. This current would be nothing but this IN. Okay? So the meaning of this IN is nothing but the current that would flow into the shorted link. We will be shorting these points A and B just temporarily for just calculation of IN. Later on we will be removing it. Okay. So the steps would be like this. We will be first removing the load resistor. We will be getting the open terminals A and B, and later on for the calculation of IN, temporarily we will be shorting the two terminals A and B, and then we will be doing some calculations, adopting some procedures so that we can determine this current flowing through this shorted link. And once we calculate that value, we call that value as IN, and in this equivalent circuit we will show that IN value as our current source, equivalent current source. And second thing, to calculate RN, it will be the same thing as we did while using the Thevenin's theorem. What is the meaning of RN? Meaning of RN is that if we get such two-port network with the two terminals open here, and if we look into this circuit, look into this box, and if we try to calculate or try to see what would be the net resistance given or offered by this entire passive circuit across these 2 points, that would be our RN. Okay, so this procedure of finding RN here will be same as procedure of finding RTH into the Thevenin's theorem. So 2 steps would be common. The first step of removing the load resistor is same in both Thevenin's and Norton's procedures, and procedure that we are adopting for determination of RTH there in Thevenin's theorem or RN here, this procedure will be also exactly same. Okay, and now once we accomplish this job, then we can represent the given circuit with the help of such equivalent circuit, and then the rest job will be a similar one, that we just connect the load resistance across the same 2 points A and B. Okay, so we connect it like this. Now this is a very simple circuit that we are getting, one current source and 2 resistances in parallel. Now what do you mean by this current source? This meaning of this current source is that a current of IN would be given out by this source. So this current IN would be flowing like this. Now this IN will be distributed in some proportion in this RN and in this RL. Okay, there is a simple formula that we can use for finding out current in RL for such a circuit. Okay, a simple formula of distribution of current in 2 parallel resistances. The simple formula would be, if we just denote this current I, because what is our final job? Our final aim is to calculate current flowing through this RL in the given circuit. So what we have done? We have converted the given circuit into equivalent one like this, and then just if we say that the current in load resistor is some current I, then we can simply write this I as what? A simple formula for current distribution. This current I flowing through load resistor would be the total current, which is IN, total current coming towards the parallel combination, then into bracket, in the numerator it will be RN, and in the denominator it will be the sum of the 2, that is RN plus RL. Now this is very fundamental thing that everybody learning the electrical engineering courses knows, that what is the current distribution into 2 parallel resistances. It is simply like this. If what is total current coming towards the parallel combination, it is IN. So IN is written here. But if we want current in this resistor, then you take the other one in the numerator and the sum of the 2 in the denominator. If suppose we want to calculate current in this RN, then we have to do one change, that IN will be same like this, but now you take this RL in the numerator and then the sum of the 2 in the denominator. But here in the theorem we are just concerned with the current flowing through our load resistor. So this will be the formula that we will use finally. Okay, so this will be the normal idea, central idea of the Norton's theorem. So let us go step by step. Okay, so I will just make the blackboard clean and then we will proceed towards the given circuit. Our first step in Norton's theorem is to remove the load resistor. That we have done. We have removed this 8 ohm resistor and we have shown or written somewhere that our load resistor is 8 ohm. That is the first step. Now the second step. In second step, what we will do is we temporarily short circuit these 2 points. I will just show it with some different color like this. So suppose we short here. So this is the beginning of our second step. That what we have done, after removing the load resistor, whatever circuit we are getting the 2 open ports, we will be just shorting them temporarily. And now our job is very simple. We use simple Kirchhoff's laws to find out current flowing through this shorted branch. Why we are doing that? Because we have defined that the equivalent current source IN is nothing but the current flowing through this shorted link. So we are interested in finding out the current in this shorted link. So we will just go by our regular procedure of using the Kirchhoff's voltage and current laws. Okay, so let us start. So let us distribute the current. Now here you are free to distribute the currents on your own. Only your final job should be, or final aim should be, to calculate the current as well as magnitude of current as well as the direction of the current through this shorted link. So suppose let us start from this particular end. For example, we say that this current is I1. Okay. Suppose I say that this current is I2. Now see, I1 current comes over here up to this node. Out of that I2 goes down. So what would be current going ahead? This current would be I1 minus I2. Now I1 minus I2 reaches here. Now again there are 2 paths. See here, now it is shorted, so it is a closed path. So we have to say use one more variable. So I1 minus I2 is coming over here. Suppose we say that the current going ahead here is I3. Now see, I3 goes here. So what current will come down? The current coming down would be I1 minus I2 minus I3. Now see here, this I3 will flow through this shorted link. So here I will say that it is I3. It will come down, then through this battery, the I3 will reach here. These 2 currents meet. And then what current will go ahead? The current here would be I1 minus I2. Now I1 minus I2 reaches here. I2 is further added. The addition of the 2 would be I1. So I1 goes like this. And you will find that our current distribution is proper. That we are again reaching the same point with the same value. Okay, so this is the current distribution. Now see here, with our current distribution, we got some current I3 into this shorted link. That means we are now interested in finding out the value of this I3 because this value of I3 would be our IN. That is the most important thing. Suppose you distribute the currents in any different way, then your current in this shorted link may be something different. So you will find that. You will find the current flowing through this shorted link only. So here we have distributed the current now. See now 3 variables I1, I2, I3. Our next job is the regular job that we have to identify the loops or meshes. So 3 current variables. So we need 3 equations to solve. And for 3 equations we need to identify 3 different meshes. Again as a regular practice, we consider that this is our loop 1, this small one. Then this middle one from this point here down left and again to the top original point. We consider that this is our loop 2. And then for this point here, then A to B, then B to back to this point and upwards. We consider that this is our loop 3. So we have identified 3 meshes like this. And then our next job is just to write the loop equations. So very fast we will write it. For loop 1. So what would be the equation for loop 1? We have assumed our direction of travel like this, clockwise for all the loops. So suppose for this loop 1, suppose we start from this point. Now this to this, it will be minus 2I1. So minus 2I1. Then this point downwards, it will be minus 4I2. Then from this point left, no component, so no voltage rise or drop. And this 2, again original starting point, it will be plus 20. So plus 20. Now we have traversed the entire loop, and this all must be equal to 0. See, every time I am insisting on revising the concepts of distribution of currents and writing the loop equations. That is very much necessary. Those who have all these concepts clear, they should directly go to the video. Otherwise, I advise or I request the viewers to see the video on the Kirchhoff's laws, so that the concepts of distribution of currents, writing loop equations, and all those concepts will be very much clear. Because for all the network theorems, we must have the entire knowledge of the distribution of currents, writing loop equations, identification of loops, and so on. Okay, so I just request to go through the video on Kirchhoff's laws first. Okay, so we have written the loop equation. Just make it somewhat simpler, and maybe we take the constants to other side. So it will be just I1. I divide all the terms by minus 2. This will be plus 2I2. 20 taken to other side will be minus 20, and divided by minus 2 will be 10. So this will be the simplest form. So we say that this is equation 1. So very fast we write the equations for other loops. So for loop 2, now our loop 2 we have identified as this, here down, left, and to the top. So this to this, it will be minus 4 times I1 minus I2. Then next, coming down will be minus 2 times I1 minus I2 minus I3. Then to the left there is a battery, but we are jumping now because we are coming back like this. So we are jumping from positive to negative plate. So here to lower potential, so it will be minus 8 here. So minus 8. And then this to top, we are coming like this. We are going to top, but the current is opposite. So it will be plus 4 times I2. So plus 4 times I2. And this all must be equal to 0. So we have to simplify the equation. Let us compile all I1 terms. Minus 4I1, minus 2I1 is minus 6I1. Those are the I1 terms. So minus 6I1. Then plus 4I2, plus 2I2, plus 6I2, and plus 4I2. So that will be plus 10I2. Then I3 terms. It is plus 2I3. That is the only term. So plus 2I3. And then this constant 8 we can take to other side. So this must be equal, this will be equal to 8. Further we can simplify if we divide by 2. So it will be minus 3I1 plus 5I2 plus I3 equal to 4. So we can say that this is our equation 2. Okay. So let us every time check whether we are writing properly in each step. Otherwise, making mistake of even simple sign plus or minus would make our entire solution wrong. So dividing by 2, minus 3I1 plus 5I2 plus I3 equal to 4. And then we have to similarly write equation for loop 3. For that I will just make use of this space. Okay. So for loop 3 now. Loop 3 now. Equation for loop 3. Now loop 3 is this one. So we take this, we traverse along this loop in clockwise direction in this manner. So from this point to this point it will be minus 4I3. Then this to this, no component, so no question of voltage rise or drop. Then B to here. Now see, we are coming like this. So we are jumping from negative plate to positive plate. So from lower to higher potential, so it will be plus 4. So plus 4 here. And then last term here, this point upwards. Now see, we are moving upwards, but current is coming down. It is coming opposite to us. And so it will be plus 2 times I1 minus I2 minus I3. And now we have traversed the entire loop, so it will be equal to 0. Making it simpler, I1 terms plus 2I1. So I write here plus 2I1. Then I2 terms minus 2I2. So minus 2I2. I3 terms minus 4I3 here and minus 2I3 here. So minus 6I3. And constant term is 4. We take it to other side, it will be minus 4. We can further simplify by dividing by 2. So it will be I1 minus I2 minus 3I3 equal to minus 2. So this will be equation 3. So we have got the 3 loop equations, equation 1, equation 2 and equation 3. Our rest job is very simple. We have to solve these 3 equations simultaneously, and now we are not interested in all the values I1, I2, I3. As per our current distribution, we know that the current flowing through the shorted link is just I3. So our aim would be just to determine I3. So you can pause the video and you can solve these 3 equations and find out value of I3. Suppose your value comes plus, then that means the current is really flowing from point A to B. If your value comes minus, that means actually the current would be flowing from B to A. But that will be apparent only after we get the value for this I3. So you can pause the video and solve the equations and just calculate what would be the value of I3. So I hope you have now calculated the value. You have solved the equations and calculated the value for this I3. See, I have written what should be the answer for the given equations. The I3 should come out to be 1 ampere. And see, the value should come positive with the given current distribution. So if you solve the equations, you will get the value of I3 as 1 ampere and you will get a plus value. It means that in actual given circuit, the current must be also be flowing from A to B. So I have written here I3 is 1 ampere and it is flowing from A to B. Really speaking, this is nothing but our value of IN, Norton's current source, equivalent current source. So this value I3, we can say that it is IN and which is having value of 1 ampere and it is from A to B. So this conclusion we want from this step. So what we are doing in step 2, that in the given 2-port network where the ports A and B were open, we are first shorting the 2 ports temporarily like this. Then we are using Kirchhoff's first and second law. We are distributing the currents in various branches. Then we are selecting the required number of loops. Then we are solving the equations and then we finally find what would be the current flowing through only the shorted branch. We are not interested in any other values. As per our given current distribution, the current flowing through the shorted branch was I3. So we, after writing the loop equations, we solved the equations and we found that the value of I3 comes out to be 1 ampere. It comes a plus value. So the actual current must be from A to B. So instead of saying I3 now, I have said that in our second step, we have calculated value of Norton's current, equivalent current IN, and that is 1 ampere. So I will write this value somewhere here like this. IN must be equal to 1 ampere. And so just we remove this from the board. Okay. So this was the second step in Norton's theorem. Now the third step is, means what is remaining now in this solution? Only the value of Rn, Norton's equivalent resistance, that is remaining. Remember, this step is exactly same as the step to find RTH in Thevenin's theorem. But let us repeat it here. Okay. Now see the circuit. For this finding out this equivalent resistance, you want only the passive circuit. So we don't want any such current distributions and all these things that we have done, because we have finished the part of finding out IN. So we have to just scratch all these things from the board. Okay. So for finding out the value of Rn, Norton's equivalent resistance, we have taken the initial circuit. Which circuit? After removing the load resistor that we want. One more thing is remaining. We want just a passive circuit. That means we don't want the voltage or current sources, or we don't want the power sources in general. What is the basic rule that I have told? For removal of power sources from the circuit, means in order to make it entirely passive, we have to adopt certain rules. The rule is that if it is an ideal voltage source, it will be replaced by a short circuit. If it is an ideal current source, it will be replaced by an open circuit. And if the sources are not ideal, if they are practical, then let it be a voltage source or current source, they should be replaced by their internal resistances. Now see our problem statement. In problem statement, nothing is mentioned about the internal resistances of these voltage sources or of these batteries. That means our sources are ideal sources. Now here in this problem, no current source is there, all are the voltage sources. So what is the rule for voltage sources? If they are ideal, then they should be replaced by short circuit. So we have three voltage sources, here, here, here. All of them are ideal sources. That's why we have to replace them by just a short circuit. So this 20 volt source will be shown like this, a short circuit here. This 8 volt source also, since it is ideal one, it will be a short circuit. And for 4 volt source also, it is also ideal, so a short circuit here. So this circuit we have to consider. Now see the circuit, remaining circuit will be just composed of the passive elements. Here they are all the resistances. Okay. Now we have to just reduce this circuit so that finally there would be one single value of resistance remaining across these 2 points. Okay. We can start from that other end. Now see, if you look at the diagram, you will find that this 2 ohm is this branch, this 4 ohm is this branch, 2 and 4 are parallel. What is parallel combination of 2 and 4? 4 2s are 8. Parallel combination of two resistances, R1, R2, will be R1, R2 divided by R1 plus R2. So 2 into 4 is 8 divided by 2 plus 4 is 6. So 8 by 6 is 4 by 3. So instead of this 2 now, we just show is single resistance of 4 by 3. So I will just show it like this. So your circuit reduces to this particular thing. So this value will be now 4 by 3. Now further we have to reduce. Now you will find that this 4 by 3 and this 4 ohm, they are in series, because see, look at this branch, this 4 ohm, and it is coming in series with this 4 by 3. So this entire branch you can replace with the series combination. Series combination is what? Just the simple addition. So 4 plus 4 by 3, it will be 16 by 3. So instead of these two, see here, 4 plus 4 by 3 must be equal to 16 by 3. So we have to replace these two resistances by a single resistance of 16 by 3. So circuit will be reduced like this. Now this value we have to show 16 by 3. Further we have to simplify. Now see here, this 16 by 3 and these two are in parallel again. See, this branch is like this, and across the same two nodes, this 2 ohm is there. So again, what is parallel combination? Product divided by sum. So 16 by 3 into 2 divided by 16 by 3 plus 2. We have to calculate it this way. So this will be 32 by 3 in the numerator. In the denominator, it will be 22 by 3. So it will be 32 by 22. So that will be equal to 16 by 11. So 16 by 11 will be the value of this parallel combination. So we can now replace both these resistances with the single equivalent value 16 by 11. Okay. So the circuit will be reduced like this. Instead of these two, one resistance of 16 by 11. So this value I write here, 16 by 11. And one more job now. See here, across these 2 points, this 4 ohm is just coming in series with this 16 by 11. So simple addition, 4 plus 16 by 11 will be 44 60 by 11. So finally your circuit will be like this. Instead of these two, it will be just one single resistor, and the value of that single resistor is 60 by 11 ohm. And this equivalent value is nothing but our Rn, Norton's equivalent resistance. Okay, so this value also we have calculated. I will just write it here. Rn must be equal to 60 by 11 ohm. Now remember those who have seen the video of Thevenin theorem, because we have solved the same problem. You will find that there also the exactly same procedure we have adopted. There it was called as RTH. Here it is called as RN. But remember, the meaning is same in both the procedures. Okay. So 60/11 is the equivalent resistance. Now we have calculated all the parameters which are required by us. Let us draw the equivalent diagram. Now the diagram would be like this. Our 2 points A and B. Then here I will show the current source. Now why only this direction? That is the question. Because we have already obtained a result that the current 1 ampere was flowing through the shorted link from A to B. Now our point A we have shown here, B we have shown here. So if we connect it like this in this fashion, then only the current will be flowing from A to B. Otherwise, suppose if you would have got this answer as minus here, negative, that means you would have connected the source in opposite polarity, this arrow downwards, so that the current would have flown from B to A. Okay, that is the thing. Now this is our IN, and this IN is nothing but 1 ampere that we have got. One more thing we have to show. We have to show Rn. It is shown in parallel to the current source. So this is our Rn, and its value is, we have calculated 60/11 ohm. And then the final thing, after drawing the equivalent circuit across the two terminals A and B, our next job is very simple. We just reconnect or reintroduce our load resistance into the given circuit. So I will just show the load resistance reconnected here, and this RL is nothing but 8 ohm. So it means that whatever was the given circuit, it can be finally replaced by this simple equivalent circuit. And the final job remaining to find the current in load resistor. Suppose we say that this current is I. And as we earlier discussed, what must be value of I? I value must be equal to the total current IN in bracket Rn in the numerator divided by sum of the two, Rn plus RL. So let us just calculate it. Putting the values, IN is 1 in bracket, in the numerator Rn. Rn is 60/11. In the denominator, sum of the two, Rn is 60/11 plus RL is 8. So this you have to calculate. Okay. So we will just calculate that value. So it will be, this 1 into 60/11 is 60/11. And in the denominator, this sum will be 88 plus 60. So 148/11. So finally it goes to 60 divided by 148. If we just make it simpler, we can divide both numerator and denominator by some common factor, say 4. So if we divide 60/4, it will be 15. And in the denominator, it will be 3, 7. So 37. Okay. So this is the final answer. So what answer we have got? The current in the given load resistor must be equal to 15/37 ampere. And also we have proved that this current must be flowing from points A to B in the given circuit. If you check the answer with all the previous procedures of superposition or Thevenin's theorem and all that, we have taken the same problem in those videos, you will find that the answer still matches with those results. So final answer is, the current flowing through the load resistor is 15/37 ampere. Now here we have calculated the things. Just one thing, that we earlier made a statement that we will make some remarks finally. Now see, the remarks are like this. Just let us switch to our knowledge, previous knowledge of the conversion of practical current or voltage sources. For example, if I have this circuit as the given circuit like this, and this value is given as say 1 ampere, then this current source is suppose parallel to a resistor of 60/11 ampere. And suppose these are some terminals, open terminals, A and B. And suppose my question is, convert this given practical current source into equivalent voltage source. Then what would be the things? We have earlier learned as basics that if such a circuit is given and if this is a practical current source, then to convert it into equivalent practical voltage source is a simple job. Current into this resistor must be equal to the value of equivalent voltage source. So 1 into 60 by 11 is 60 by 11. So the equivalent voltage source would be this 60 by 11 volt. And the same resistor which is in parallel with the current source, that must be shown in series now. So we will show the same resistor 60 by 11 in series with this voltage source, and then points A and B will be located here. So it is a simple thing to convert the sources in this particular fashion. Also we can do similar way for conversion of practical voltage source to current source. Now if you look at this, all these values that we have got, we will find one thing, that this was our Norton's equivalent circuit. Now if you check the solution with Thevenin's theorem, we will find that this was the equivalent circuit that we got in the Thevenin's theorem. That means if you solve any such problem with one of the theorems, either Thevenin's or Norton's theorem, and whatever circuit equivalent circuit finally you get, and if you convert that circuit into other type of source, then you will find that, suppose you solve the problem with Norton's and you get some circuit like this, and suppose if you convert this circuit into equivalent practical voltage source, you will get exactly the Thevenin's equivalent circuit. That's why it is said that Thevenin's and Norton's theorems are complementary to each other. So this was all about the Norton's theorem. Again, I mention here that a lot of practice will be needed on different types of problems. Okay? And once we do a lot of practice, then we can get real mastery on solving this type of problems. Thank you so much.